The random access procedure contains several steps. First of all, a knock-knock. The random access preamble is sent by the UE, which means "Hello, network, here I am." The preamble itself is a sort of choose sequence which is sent on the physical random access channel. 6 adjacent resource blocks out of the available bandwidth are occupied by the preamble, but where these resource blocks are located is configured by higher layers via the system information. Based on information derived from system information block type 2, the UE also knows in which subframe a specific one or all in that radio frame the preamble can be transmitted and which preamble format to be used. At all there are 5 formats, where the first 4 are applicable for LTE FDD and LTE TDD, and the 5th one just for LTE TDD. The different formats are necessary to bridge the gap between the base station and the UE. After the UE has sent the preamble, it waits for a response from the network. If no response is received, the UE increases the power level with which one the preamble was sent. If the eNode B has received the random access preamble sent by the UE, the random access response comes on the physical downlink shared channel. This response includes uplink timing adjustments, instructions, initial uplink resource grant required for transmission in step number 3, and an assignment of a temporary identity. In the next step, the step number 3, the UE first time uses the physical uplink shared channel. The transmitted information includes, for example, a radio resource control connection request, tracking area update, or scheduling request. It also includes the allocated identity. Step number 4 marks the contention resolution. The random access procedure can be verified using Rohde and Schwarz CMW 500 LTE protocol tester step by step or as a complete procedure. The instrument is ready, and so testing depends completely on the implementation status of the device under test. With passing the random access procedure, the UE is known by the network and would be able to transmit and or receive data. We know already that data in LTE, it doesn't matter if it is system or paging information, so control data or user data, is transmitted via the physical downlink shared channel. As the name implies, this channel is shared between all the UEs in the radio cell. An particular UE is interested to know if it is addressed with data and where to find this data. Another UE is looking for the radio resource blocks carrying system information, and so on. The device needs to be informed about the scheduling decisions, and therefore all devices need to read the physical downlink control channel. This channel is transmitted over the entire bandwidth in the beginning of each subframe. Via unique identities, information are provided to the UEs if they are addressed with data and where to look at on the physical downlink shared channel. But of course there might be more than one UE in a radio cell, and all of them needs to be addressed with control information once in a while. Therefore the amount of resources means how many OFDM symbols in the beginning of a subframe are occupied by the physical downlink control channel might differ. The UE needs to be informed about that. This information is provided to the UE by another channel, the so-called physical control format indicator channel. This channel, transmitted on defined resource elements on the first symbol of each subframe, contains the information how many OFDM symbols are used for the physical downlink control channel. Depending on the bandwidth used in this cell, the number of symbols differs. In case of a 10 MHz channel, respectively 50 resource blocks, at minimum 2 OFDM symbols are used in the beginning of each subframe, at maximum 3. 4 OFDM symbols are reserved for future use. The hybrid automatic repeat and request for LTE in the downlink works the same way as for HSDPA. The UE can request the retransmission of incorrect received data packets via ACNAC reporting. The ACNAC information is sent in the uplink on the physical uplink control channel, PUCCH, or the physical uplink shared channel, PUSCH. This depends if in parallel uplink data transmission is ongoing or not. The ACNAC sent in the uplink refers to the data packet received 4 subframes, means 4 milliseconds earlier in the downlink. This is a timing relation in LTE FDD. In TD-LTE it is a little bit different. Here the timing relation depends on the uplink downlink configuration, means how many subframes are allocated for downlink transmission, how many subframes are allocated for uplink transmission. Because of that, a single ACK-NACK response for providing HARC feedback could be used in TD-LTE for multiple PDSCH transmissions. As we learned, Evolved Packet System, EPS, is efficiently a connection-oriented transmission network, and as such it requires the establishment of a virtual connection between the UE and core network, respectively Packet Data Network Gateway, before any traffic can be sent between the UE and the network. This virtual connection is called a EPS bearer, a term that emphasizes the fact that this virtual connection provides a bearer service, means a transport service with specific quality of service attributes. The EPS bearer corresponds to the PDP context used in GPRS wideband CDMA. The EPS bearer has to cross multiple interfaces to establish that connection. Between the UE and the eNode B, between the eNode B and the serving gateway via the S1 interface, and between the serving gateway and the packet gateway. A lot of procedures have to be executed and a lot of information are exchanged between network and the UE. As shown, tasks like the initial access procedure have to be passed first, further RRC connection establishment, attach request and PDN connectivity request, authentication and non-access stratum security procedure, checking the UE capabilities, access stratum security, RRC connection reconfiguration, attach accept default EPS bearer context request, and as a last step the default EPS bearer context accept.